When a nerve cell sends a command for muscles to contract, all of the muscle cells which it touches contract. All of the muscle cells which are then tied to any one nerve cell are then referred to as a motor unit. So in this animation, whenever a nerve cell in yellow goes pink, that simulates an electric action potential. All of the muscle cells which it touches, which are its motor unit, all of these cells would then contract. Now, motor units vary. In some parts of the body, the number of the number of muscle cells in a motor unit may be 1 or 2 or 3 muscle cells. These are very small motor units. Places like the eye, the fingertips, the vocal cords, thus have very precise control. In contrast, places like your back or your calf, these areas have motor units which may have hundreds or thousands of muscle cells touching one nerve cell. So when a nerve cell sends an electric message to contract, its whole motor unit then responds, whether there be 1 or 2 muscle cells in a small motor unit or hundreds of muscle cells in a larger motor unit. One of the ways that we can change the amount of force which we generate in a muscle contraction is to change the number of motor units. If we only use a small number of motor units, we would generate a small amount of force. Say we were lifting something light. If we wanted a much greater force, we could use a larger number of motor units or all of the motor units in a specific muscle. So we can change the amount of force we generate in a muscle contraction by increasing the number of motor units which we use. In what is known as a muscle twitch, a nerve cell tells muscle cells to contract, they contract, and then they relax fully. However, the messages from a nerve cell can come in faster than what a twitch would allow. In other words, that before a muscle cell is done relaxing, a second message to contract could come in on the nerve cell. So what would happen is a muscle cell would partially relax before it started a second contraction, and then potentially partially relax again before it started a third contraction. This is what's known as wave summation, when the increased frequency of nerve cell messages do not allow muscle cells to completely relax. Now, to take this to an extreme, and this is normal in exercise, we can see something known as tetanus, where the messages from the nerve cells are coming in so quickly that the muscle cells get no time to relax and simply maintain a state of sustained contraction. This is known in tetanus, and this is normal during exercise. Thus, one of the ways that we can change the amount of force we generate in a muscle contraction is to change how frequently we stimulate muscle cells. We can stimulate them more slowly, allowing them to fully relax, or we can allow them to undergo tetanus, where we stimulate them so quickly they have no time to relax and maintain a state of. If we were to lift something, say with our arms, we could extend our forearms and stretch our arms out as straight as they could go. We could bend our forearms or flex them and hold our forearms, close to our chest. But neither of these would be our ideal positions to try to lift something heavy. We would probably extend our, forearms and have them flexed somewhere between these two states. The reason for this is as we vary how long sarcomeres are, and obviously as we either flex a muscle or stretch a muscle, we're changing the length of the muscle and thus the length of the sarcomeres. This affects how many myosin heads can attach onto the actin filaments. When a muscle is very, very long, then fewer myosin heads can contact the actin filaments, and the same would be true if a muscle was very, very short. So to generate the maximum level of force, there is an ideal sarcomere length. If we were to stretch our sarcomeres longer than this or shorter than this, then we would be able to generate less force. So in the generation of force, we can change the length of sarcomeres, and there is an ideal length at which the greatest force can be realized.